Years ago when Shimano released their second version of Di2 on the Ultegra 6700, I believe, they introduced a new technology they called E-tube. And what it really was, people didn't quite understand what E-tube was. And I think to this day they still don't. E-tube is actually the term for their data over power line system. And what that enabled you to do is you could plug anything into anything. It's just two wires. Now, there might have been some requirements for those wires, but you could plug a derailleur into a shifter, and the shifter into a splitter, and the splitter into a battery, and into the other derailleur. And it could be wiring madness. Now, realistically, all bikes were basically wired very similarly. Shifters into interface, interface into a junction box to two derailleurs, and a battery. But you didn't have to. And that was the beauty of E-tube. It made me fascinated with this idea of having a two-wire system, because it's very easy to make a two-wire connector, but once you add a third, well, you either have to do ring connectors or you have to do three prongs and they have to plug in, and then there has to be indexing. But two makes everything easy. So I had this fascination with it, and I've made several attempts at looking at it. In fact, I have connected my bike to my Di2 bike to an oscilloscope a couple of times and tried to figure out what was going on. I've disassembled derailleurs and shifters, and I've tried to trace back the circuits. And it still isn't obvious to me now, and I don't really have a reason to truly reverse engineer it and waste hundreds of dollars on derailleurs because you will break them, or you will at least destroy the waterproofing. But I've been fascinated by this idea, and I keep stumbling into this same website, Electronic Design, with an article from 2013 from which a person submitted, and they had built years earlier, and there were actually some revisions to it over the years. It's an interesting schematic, and it looked very daunting to me at the time. Well, as my electronic skills have improved, it's actually still like a super simple schematic. It's just I didn't understand what was going on, and I'm not going to build something I don't understand. And years later, I started looking into it again, especially with new chips started coming out that did data over power line, or power over data line, whichever. Surprisingly, true wireless earbuds, the housing, or the little like charger pack carry case thing, they need to talk to those earbuds, but they don't want to add multiple pins. Those pins are actually more expensive than chips. And so several companies have come out with some chips that talk over power lines, and I got really excited. They're not very fast, but they are super wasteful with power. Like sending a bit during the periods we were sending bits is about 50 milliamps. I'm like, it is hugely wasteful, but it's because they don't need to talk very much. You only need to initiate a handful of bits going back and forth, and they're happy. So that brought me back to looking for circuits and schematics. I had a couple of ideas, but since this was the original one and it uses a very simple frequency method called on-off keying, which basically means when it's on or off, depending on which way you want. Either it's AC coupling a frequency to the line, or it's not AC coupling frequency to the line. Compare that to frequency shift, where you're AC coupling a frequency to a line, and then for a 1, and then a slightly different frequency for a 0. That is a little more complicated, and then you get into phase shift keying and quadrature phase shift keying and quadrature amplitude modulation, and like it keeps going on and on and on. But those aren't simple, and I didn't find any simple ways of just kind of getting them to work. Now, there is one other simpler method of why don't you just capacitively couple UART directly to the power line. I know why that won't work, and it's because the bit length is so long and they start decaying, and then when you drop, you go negative, and you need something there. But there are now reference schematics that say you can do that with RS-485. So I might try that, but it looks like it requires big caps and big inductors and big common mode chokes and a lot of stuff. For now, I'm going to start looking at this OOK, so on-off keying, power over data line, PoDL. So the OOK PoDL, it's an OK PoDL. And first I'm going to explain that with some drawings, and then I'm going to go through my experiments with it. And I had pretty good results. So originally I got this design. I found this on the internet, someone who had tried this many years ago, and they did a really good job doing it. This is one of the first ones I found, but I really didn't fully understand it at the time. And I've more or less sat down to figure out how it works. And this is my first attempt at this, so I replicated it in Altium. And so in order to understand what's going on here, we need to kind of divide this into little chunks, because this is actually about 4 or 5 different elements. So on the transmit side, we have a carrier, and that's just going to be a square wave. And we're going to do that with some sort of clock generator or our 50% duty cycle PWM or something like that. But you want to the faster this is, the more data you can really carry. But you'll have to tune your peak detectors later. So this all goes into a output enabled buffer, and so the UART actually goes into the output enable, whereas the carrier actually goes into it as the input. So when there is UART signal, when the UART is active, you get the carrier passing through, and when the UART is inactive, nothing passes through, it's back to 0. So it's basically vibrates when there's a 1, and it is nothing when there isn't. And actually that's going to end up being backwards, because this is a not output enable. You can see that line on the top. So if we have a 12 volt nominal power line here, this is going to AC couple onto it, and we're going to spike up when we get a leading edge, and then it'll slowly decay, and when we flip it back, it's going to jump down basically how much we decayed. So if we are plus 3 volts and we decay down to 0.15, or sorry, 1.5, and it'll jump down lower 1.5. And then so that eventually causes you to average out. So you basically will end up with this superimposed signal that averages around 12 volts, but will be plus or minus a bit whenever that not output enable, so whenever the UART TX is actually low. And so now we have to recover that signal. So we've got our power line coming in with all those little squiggles on it. And this filter cap C102, that's going to pass only the AC in theory. And so we now have just the AC component shifted down. Great. What we need to do though is first we need to clamp it for protection. There is a possibility, especially with strong leading edges, and if we couple a higher voltage at some node, you could get higher voltages here. So basically we could clamp it to a more tolerable amount. So these just act as a kind of a clamp that kind of add min-max based on their forward voltage. Great, so now we have clamped. So we kind of squared off the edges if they were around it, but we have a fairly square carrier in our digital case here. And these two elements circled, they're the peak detectors. And what our peak detectors are really kind of like those VU meters on stereos. They go up really fast and then they slowly decay, and as you get little pulses, they kind of average out. So, but before that, they have to pass through these diodes, because we don't actually want negative voltage. We're in any of this, we'd have to add some more circuits. So we're just going to chop off the negative bits. Great. So now we're left with this. And so you can see that there is no inline resistor after that diode. That means you can charge the capacitor as fast as you want, but it has another resistor to dissipate the charge in the capacitor. So combination of the RC circuit here, the time constant of that relates to how fast it decays when you turn off. And so something like this, you want it to decay relatively fast, but before it gets to the next bit, you don't want it to be zeroed. And so it goes up really quickly and throughout all the bits. It'll average out to be somewhere in the midway, and then drop when there is no data from the UART, basically. So when the carrier, you want it to be able to come up within one or two cycles of the carrier, but you also want to fall down in a similar vein. This one, however, you want it to be slow. So even when the carrier stops, it only slowly decays. So you can go multiple bits and many multiple cycles of the PWM before it decays. So you'll notice it's a much bigger capacitor. It's about 100 times. And now we have a voltage divider that is also much higher, so about 100K. We're also pulling it up to VDD and RF, so the 3-volt line. That's so that we don't end up in, we always want it to be pulled a little bit high, but not too high. So it's a very, very weak pull up. I honestly don't completely understand that, but it seems to work, and I'll dig into it later. But when we have those two signals, you can compare them, and we compare them with standard comparator. And oh, it looks like we recovered our UART from all the way back here. So, I mean, I got the scale a little wrong, but yeah, the TX on and off, well, we recovered that. So that's basically how all of this works. It's pretty simple.
If you look really closely here, it's called the PoDL OOK. Actually, the PoDL OOK. Power over data line, on-off keying. We vibrate when there's a 1, and we're going to use the PWM output of a microcontroller to do that. And when there's not, it's a 0. For this experiment, we're going to try and build 4. So I want 1 to talk, 1 to receive, 1 to snoop, and a spare because I'm going to screw something up. Paste these just by dabbing paste, and then I'm going to reflow them with the hot air, and we'll see how that goes. The op amp I use, which I don't actually need, yeah, there's an average and a bit line. So these ones down here, and those can go into a comparator. I put a comparator on it, but because I didn't fill in my circuit board or my schematic properly, I had the wrong part number, and I had to have a little bodge. The first thing we've got here is just using my oscilloscope. I've written short version, start clock, wait till the clock is started because that can take a little while. Set up a timer to pre-scale 0. The minimum out we can get is 1 by setting a count of 1, and then it will reset. For the GPIO, configure a task on that pin number so that the task will toggle it. Then link the event from the timer to the task, which we created here, that will toggle the pin on and off, and set the channel number for that, I believe. I'm not 100% sure there. And then we just start the actual timer that we set up here. And then that brings us over here, and I set it to pin, I believe 22, pin 22, and we've got our clock. So now we can get our OOK board and see what's happening on the output. So let's turn it back on, see if we still get a carrier. All right, great, we've got our carrier. Now we can start probing. So we've got our 5-volt line here. You can see 2 volts per division, so 1, 2, 2.5. Great. Now let's capacitively couple. Oh, so now we're getting about, it's still averaging about 5 volts, but now we're getting about a 0.5 volt swing capacitively coupled. Now, we still have our 5-volt line. My transmit is pulled high, we get nothing. And then when it's pulled low, like I'm there, we get capacitive coupling. Nothing,
capacitive coupling. So we're definitely transmitting, but now let's, instead of at this line, let's pull at this side. So now we're plugged into ground. I'm going to take my other board here, grab onto his ground, grab onto his power line. And we're still, so now we are transmitting. We've still got our 5 volts, still getting information. But then if I do this, no information, coming, information, no information, information, no information. Horizontal, yeah. So our transmitter works. And you know, it's actually surprisingly a lot flatter here than I thought it was going to be. The reason I thought, like, we have a pretty low capacitance in the nanofarads that we're capacitively coupling now. I'm not doing any current measurements right now. Now is an interesting point where I think I'm going to go get another probe and see what the data out says and the power output. So my purple is my output. I'm currently grounded. Now I currently have power. Grounded, power. So when we're grounded, we're vibrating and we get this low signal, and then we're not vibrating, we get a +1. Or sorry, in this case, 3 volts. So up, down, up, down, up, down. So we're not vibrating. The output of this peak detector, which I explained hopefully earlier, is giving us the right signal. So this is actually really good. Now what I want to do is see if I can mess it up with a small load. I'm going to go get an electric motor. There's very few things that I can think of in life that are more noisy on a line like this than the motor. So I'm gonna try and do some repositioning. This might be a little too much current for that little inductor. I think I've run through the inductor. Hold on, let me check if I run through the inductor. I've got to run through the inductor. Yeah, of course. So this is the reference schematic, and I'm coming in, my power line comes in, then it's filtered, and the filtered, and so for the most part, it looks like it's working, but it does seem noisy. I was making a mistake. I was connecting the motor to the actual power line communications, but I need the motor after the inductor. So I put a big cap on it, but ta-da, no big deal. So we're still capacitively coupling onto it with our, so this is our 5 volt line. You can see we're wobbling around, we've got signal. And on the other side, it's filtered out. So we're sending in ground, so we're getting a ground out. So we're sending in 0, we're getting a 0. And then when we increase it to 1, we're getting a 1. So you can see that jumped. So 0, 1, 0, 1, 0, 1. But we like to see it capacitively coupled. So that's working well. Interesting. I think I need to write some new code now to get some UART through it. And I'm going to see if I can use the loopback code. So we're triggering off the 3rd channel, which is the received line over here, this purple one. So right here. These are 2 development boards. This is fully erased. This still has the UART code on it. We're using the output from the Sager chip here, which is a programmer but also has a built-in UART. And it's physically tied to that chip, but it doesn't matter. So we're using its transmit out to go into here because we also need that carrier frequency. We need that 8 megahertz clock. 5 volts power coming all the way over through a bunch of wire. From there, we're extracting the 5 volts, regulating it down to 3. Then we have our circuitry, and then we have our receive circuit here. So I'm just going to send
a single character. I was already testing this, so hopefully everything should work. So I got an A, and you can see I got signal here. And if we zoom in, you can see how it goes. So signal slowly is rising back up, but it's enough that that basically we're getting stuff through. So if I say, type in, this is a test message, and I send it through, then you can see how we're getting all these back and forths. So we're getting our standard UART. I'll just do that one more time to get a longer capture. So there's lots of bits here. They're being recovered. That's great. So we're completely getting it through. So let's add some difficulty to this. Let's add back in the motor. And I'm going to do it on the far side. Let's do it without the big cap first. Remember, these terminals after the inductor. And wiggly wires aside. So now we're getting some wiggly noise. We just saw it come up here, and this is a test message. Every single time, it's getting through very reliable, and we're at a very fast bit rate here. We're at 115.2 kilobit per second with an 8 megahertz carrier, and it's getting through. So now with that, we're pulling current. You can hear the motor going. We're still getting messages. Let's add in a third node. So I'm going to come off this guy. I gotta bring this all downstairs, solder on a node, and then let's connect just a little FTDI that I've got here. This is my should be a 3.3 volt one. We have a 3-node setup. The primary node is back here with that board generating the carrier, and because of that, it can't truly receive. Then we have it goes all through the spaghetti to the second board, which then goes to this DK over here. Hopefully I won't lose any connections. And then it goes from the second board to the third board to the FTDI. So the power goes through the power line through the first board to the second board, and it's powering all the electronics on board. So that's all going. There is current going over the power line, only a few milliamps. Now, what I've been finding is now that I've added 3 nodes and I've made cables longer, there is a bit more of a possibility of corruption. This guy's kind of ignored. So the first one, and keep in mind, 8 megahertz carrier, 115 kilobits per second. And I'll show you why that matters now. So broadcast from the first guy, so from him, the other 2 can receive because they're both set up as receive. The second one, this guy, he can send and receive. This guy can only really send. So it says I'm the first node, and so that's being looped back in. So they're sharing TX and RX. There's only one data line. So it's getting a clean signal back. That's great. But there's some first letter corruption here. Not great. And it has to do with the lag on the peak detectors, I believe. This guy yells, I'm the second node. First node sees it. So this guy, back to here, he can only receive, or he can't really receive, he can only transmit, and like we're getting good data here. So the second one, he's getting some corruption, and it seems fairly consistent. So we're having some bit flips here. Correctable with some sort of checksum, or detectable with a checksum, correctable maybe with a CRC. Now, unfortunately, because of how this NRF52 is actually programmed, I can't change its baud rate. So just ignore this guy. But what I'm going to do is I'm going to disconnect, drop the speed down to half, and drop the speed down to half. And now, good bits all day. However, this guy, he'll garble because he's at the wrong baud rate. And you could see that there was a little error right here. So he sends stuff, he trips him out, and he gets really angry. But this guy, he's the first node all day. No, he's actually, well, he's sort of the second node. And this guy over here, he's really the third node. And so we're getting good signal, and now, I'm going to stick with 5700 baud, and then we're going to steal power, and we're going to see how well they talk. So we didn't get anything there. I'm the second node, I'm the second node, I'm the second node. Still getting nothing. And like, you know, I can be here. I need some of this. And even with all that sporadic connections, still getting data. So I've successfully made basically an on-off keying capacitively coupled data over power line 56K modem. I just put dial-up on a bicycle. It's actually not that bad. I mean, for most things you would actually want to do with something like this, such as turning on lights or shifting or turning on a camera remotely, or those things work. And it's so low power. I could run all the circuits off of a general purpose IO on the Nordic chip, which means, you know, when it's on, it will take like 300 microamps, because all three were less than a milliamp. It'll take 300 microamps to run that transmission, plus maybe another 500 or 600 for high frequency clock and timers and stuff like that. So it's very low power, and if you're duty cycling it, it's basically nothing. It's less than using RF, which is great. So I could generate a network for a bicycle, but keep in mind, like, you can transmit amps of power on these power lines. So you can't run like an e-bike, but you could run derailleurs off of it. You can run actuators, small servo motors. I'm not saying that I have ideas for small motors on a bicycle, but maybe I do. So hopefully you learned a bit about how that on-off keying works. I'm still not convinced that Shimano uses CAN bus in eTube. I just didn't see it when I hooked it up to oscilloscopes, but maybe it does. I think it's an unfounded rumor at this point. I still think eTube is fascinating to me, even though Shimano is definitely moving away, even though probably the pros still using wired so that they can get that extra 50 to 100 milliseconds of shift latency away. Wired wins every time. So there's a bunch of cool stuff. Hopefully you learned something, and maybe down the road I could somehow shoehorn this into the EPX project so that I can add some expanded features, or not. There's also a couple of reference docs that I've seen for new chips, for talking to wireless earbuds to talk to their cases through 2 pins. That's surprisingly one of the motivating factors of data over power lines. Remote stuff doing 10 megabit Ethernet on 2 power lines, so they're actually capacitively coupling to power lines. That's coming up. These things are much more advanced, and surprisingly, that earphone method, very power hungry. They've designed these things to be very inefficient. 50 milliamps while talking. You'd think for things that require batteries charging other batteries, yeah, but bad designs, but they probably only need for like authentication for charging. The other reference docs for capacitively coupling RS-485 onto power lines, and a similar method might be able to be used with CAN bus. However, based on that these documents are a bit old and they've been supplanted by new chips that do
on-off keying by TI on RS485, specifically for capacitive coupling to power lines. I'm guessing they don't work very well. I might try them. I bought some inductors and capacitors and COM mode chokes to try it out, but if it doesn't work, it'll probably never become a video. So with that, again, hopefully you learned something, and look forward to some more progress on the EPX project. Take care.